All right, in our second video, we're going to be looking at using technology, so your calculator, to find the line of best fit. It's also called the regression line, or sometimes they'll call it the least squares line. So, looking at this example, we're looking at winning zucchini lengths at the state fair. So, depending on the year we've got the length of the winning zucchini at the state fair. This would be our bivariate data. We've got one set of data up here, that's the year. One set of data down here, that's the length in inches of the zucchini. So, part A, we need to make a scatter plot of the 10 data points. Let the X value represent the number of years after 1985, and Y represent the winning length that year. So if this year is 1986, that's technically 1 year after 1985. So this is our X, this is our Y. Our X would be 1 in this case, and our Y would be 31.8. So we'd go to Y up to 31.8. That would be our data point. For this one, we'd be at 2 years after, we'd be at 32.9. So it would be somewhere right here. 3 years after, we're right at 30. So that one went down. 4 years after, we're at 32.7. So not quite as high as that other one. 5 years after, we're at 34.2. That's going up a little bit. 6 years, 33.6. So it'll be about right here. Then 34.5, right there, 36.3, a little bit over, 34.4, about right there, and then 35.5 put us right about here. So it looks like this data is kind of all over the place as it jumps up, but we can kind of see it. It kind of trends this way upwards. If there was a line, it would probably look something. I'm going to use a red line to hopefully have it show up. It looks like it would kind of be trending like this. So still moving up, but not necessarily going through all these points. Okay. Now we're going to use technology to perform a linear regression. So what that means is we're going to be plugging in all of this data, and we're going to have the calculator find out what this line of regression or line of best fit is for us. Okay. So I'm going to get rid of this line. Hit back on that. And this is how you would plug it into your calculator. With a TI-83 or 84, you would go into data mode. You would enter in for line or list 1 all the X values, so 1 through 10. For L2, you would write in all of the lengths, so in inches. So like the 31.8, the 32.9, the 30, the 32.7, and so on. Then step 2, you would go to Stat, and Statistics. Calculate, C-A-L-C. We want linear regression, so AX plus B. In this case, actually, we think of it as MX plus B. Then hit Enter, and it'll give you all of this data here. We're looking for a Y equals something times X plus B. Well, this A value, that's our M, would be given on the screen. This B value, right here, would be given on the screen as well. Okay, so this would give us the line of best fit, or at least the equation for the line of best fit using a TI-83 or 84. Now some people I know don't have a TI-83 or 84. They have the Casio FX9750. Now mine is not exactly a 9750. This is a 9860, but they're going to look very, very similar. I know these buttons look a little bit different from what you have, but the basic calculator functions are going to be pretty much the same. Now, this was a software thing that I downloaded and found, so unfortunately there was not a 9750 available. This is the best I had, so we're going to work with it. So for you guys with the Casio calculators, we're going to hit Menu. We're going to make sure we go over to Stat. Okay, so we're looking for statistics. Hit Enter on that. Okay, we did this before when we were finding mean, median, mode, and standard deviation. In list 1, we're just going to put in all of those, like the years. So 1, 2, 3, all the way down through 10. We need to make sure that there are 2 variables here. Oops, I got off somewhere, didn't I? 1, 2, oh, I missed the 4 right here. 4 goes here. Then 5, oops, not 45. 4, then 5, then 6. Here we go, now we're on. I'm off again. Well, this should be an 8. Enter. This one should be 7. There we go. I won't make you sit through the next one. I will fast forward our way through it. From here, though, just hit over, and you'll get over to list 2. This is where you start putting in all those other values. So like the 30.7 and so on. I'm going to pause the video right here while I type in the rest of it. Okay, we're going to continue the video then. This first one, just as a head up, I think I typed in like 30 something before. It's actually, oh, I typed in wrong again actually. It should be a 31.8 is what this very first one should be. And then we go from there. There should be a 32.9, 30, 32.7, 34.2, 33.6, 34.5, 36.3, 34.4, and a 34.5. From here, now that you have your two lists, list 1 and 2, both going down to 10 different places here, we're going to want to graph this. Well, actually, no, we want to hit calculate. So hit F2 to calculate. We're not going to want a 1 variable or 2 variable set of statistics. We want the line of regression, REG. So hit F3. We want it just in terms of x, not x squared or x cubed or x to the fourth, just in terms of x. So hit F1, and we want ax plus b, not a plus bx. We want ax plus b. So hit F1 again. What that gives us is the same ones that we saw on the screen for the TI-83 or 84 calculator. Our A value was this 0.485 something. Our B value was 30.3 or 92. So we're going to use those two as our M and our B for our y equals mx plus b equation. So we're going to take that and we're going to go back to our problem then. So from back at this screen, here is our m value, that's 0.48 times x plus 30.92. This is our line of best fit, the linear regression we were looking for. This 30.92 tells us that we're going to start here at 30.92. Right there is going to be the starting point for our line. This m of 0.48 means that, remember this would be like the same as saying 48 over 100. It's 48 hundredths. So it's like going up 48 and over 100. Means we're really not going up that much. It's a pretty flat line. So it's going to look something like this. I'm going to use red again to show it. It's going to look over something like this. So this would be our line of best fit. This y equals 0.48x plus 30.92. So we graphed our equation. We found the equation, then we graphed it. Now we want to predict the winning length for the year 2000. Well, 2000 is going to be 15 years after 1985. So we would just plug 15 into this equation. When we do that, that would give us y equals 0.48 times 15 plus 30.92. This whole piece would become 7.2 plus the 30.92. So in the end, it would all come out to 38.12, which makes sense. If we were 15 years past here, we would be somewhere over here at about 38 and some extra inches there. So that would be the winning size of the zucchini at the state fair. So we looked at how to do it on a TI-84. We did it on the Casio as well. Now let's talk about correlation versus causation. The correlation coefficient, R, is a measure of how well two data sets form a linear relationship. It's the strength. It also describes the direction of the relationship. Now this R will pop up when you run it on your calculator. You'll see R and an R squared. The R is really what matters here. So, for example, let's look at all of these scatter plots. Now, although there's not the axes on the sides here, but we can kind of look at the data and see what they mean with the correlation here. So note, the pattern begins to form a more linear relationship when the value of r begins to get closer to -1 or 1. The sign of the value just shows the direction it would go, either up or down. However, don't mistake it for a slope. They are different. So just because it's a -1 doesn't mean it's a slope of -1. That just means a negative correlation, it's going down, and it's a really, really strong correlation. A positive one is going up, and it's a very strong correlation. So when correlation is 0, there's no pattern here. They're just all over the place. When correlation is positive 0.5, you can kind of see they're a little bit going upwards, but they're still kind of all over the place. When correlation is 0.9, they're a lot closer together, definitely trending up. So that 0.9, they're really, really close because it's positive going upwards. So in this case, it kind of looks like they're going down, but they're still kind of all over the place. So it's a -0.3. It's not that strong. -0.7, they're getting a lot stronger and they're still moving downwards. For this one, -0.99. That's so close to 1. If it was 1, it would be pretty much an exact straight line. But this is very, very close, so it's a very strong correlation. It happens to be negative. It's going downwards. So causation is when someone looks at a relationship and concludes that one variable can cause the other to change. Scatter plots may give a strong correlation measurement, but it doesn't always mean that there is a causational relationship. Only careful studies can decide if there is a causational relationship present. And here's an example of what that would look like. So if we look at our scatter plot here, we have our shoe size and our reading index. This basically just says how well a student does at reading. So when the shoe size was really low, they didn't read too well. The higher the shoe size, the better the child was at reading. So according to this, if you have a bigger shoe size, bigger feet, you must be better at reading. Okay? According to this, if we believed that there was a causational relationship. Right now we can just see correlation. We would be implying causation. So notice that there is a strong linear relationship between the shoe size and reading ability. One can assume that the R value would be very close to +1 because it's going upwards. However, even though there is a strong linear relationship, we cannot conclude that shoe size causes somebody or one's reading ability to change. Just because they have a bigger shoe size, that doesn't cause them to be better at reading. In this case, there is what is called a lurking variable present. A lurking variable is a variable that is to blame for the linear relationship. So in this example, what would make a child's shoe size to go up and their reading index? Well, it would probably be age. For this example, the lurking variable is age. As a person grows, obviously their shoe size is going to grow and their reading ability should also improve. So it wasn't really that their shoe size affected their reading index, it was that their age affected both of those. So correlation does not mean causation. Just because these look like they're going up, that doesn't mean your shoe size caused you to have a better reading ability. Correlation does not mean causation. And that'll actually end it for our last video.